Welcome back to Techonomics from Cyclotron Road. So in our last video, we modeled a manufacturing process for a high-performance frisbee, and we learned that the cost of a critical raw material, a polymer called superspin, was killing our economics. Rather than just throw in the towel though, we decided to reach out to the polymer manufacturer, Plastico, to see if they could help. As it turns out, Plastico is actually developing a new lower-cost process for making the superspin polymer, but it's not yet commercial. They suggested that we could potentially add our frisbee manufacturing line onto the back end of their forthcoming pilot plant, though. To kick off the discussion, they offered to give us a quick presentation. Hi, this is Chris with Super Frisbee.
Hi, Chris. This is Beth with Plastic Co.
Hi, Beth. We have everyone here, and we're ready for your presentation.
Great. Well, I'll get right into it then. A little bit about us. Plastic Co. has over 25 years of experience in the polymer industry and patent rights to the superspin polymer, which you said could be a great material for your frisbee. Super Frisbee has visibility in the sports equipment market and a high-performance consumer product that would showcase the value of our superspin polymer. With a joint venture, Plastic Co. could supply a customer with the product from our pilot plant and also get brand visibility in a growing market. Super Frisbee would get a guaranteed low-cost supply of polymer and the option to acquire the process equipment after Plastic Co. gets the scale-up data it needs. So it could be a great deal all around. So let me show you some high-level outputs of our production cost model. We expect all-in cost for the polymer to be $4 a kilogram. This figure includes raw materials, labor, utilities, depreciation, administrative, and other relevant operating costs. We estimate the system will cost $2.5 million and would have a payback time of just under 3 years, assuming a market price for the polymer of $7 a kilogram, which is conservative. So this slide shows the user interface of our model. You can see that user inputs are the gray cells, and the results we just talked about are all listed on the right-hand side. On this slide, the tornado diagram shows the effect of varying several important input parameters from worst case to best case values. So you can see that single pass conversion and reactor pressure both have the potential to significantly affect our cost. However, we've worked really hard to mitigate these risks through lab work, and we're confident that we'll be able to operate within the ranges shown here. The market price of monomer also has the potential to significantly affect our cost, but even at the high end, Plastic Co. still expects the all-in cost to be below $4.20 a kilogram.
Thanks, Beth. This sounds like a really interesting opportunity. If we might end up acquiring the pilot equipment at the end of the project, I think we'd like to take a closer look at your cost model. Would you be willing to share that?
Sure, I'll send that right over. Thanks, Chris.
All right, here's Plastico's model, and this is that dashboard page they showed us. It's nice being able to interact with the user input and results in one location. Some of their inputs are related to the process, like production rate and utilization. Some of them are related to what they're seeing in the lab, like reaction data, and some are costs for things like raw materials and energy. We're going to drill down behind the scenes to see how they got from the lab data to profitability metrics. But first, let's take a look at how this model is structured. At the ground level is the process model. This page has a process flow diagram for a commercial system, showing pieces of equipment and material streams flowing between them. They use what they know from the lab and engineering literature to then estimate the flow rates for each of these streams. So Plastico's process contains 4 pieces of equipment. The equipment sizing page estimates some of their important characteristics, like the volume for the reactor, the power used by the compressor, and the heat transfer area for the heat exchanger. They'll need to know this information to estimate capital and operating costs in the coming pages. This model is going to estimate the total cost for the plant based on the costs for its major equipment. So first, those major equipment costs are estimated on this equipment costs page. And next, on the CapEx page, they estimate the total plant cost using correlations based on data from similar plants. Okay, now let's move on to operating costs. On the OpEx page, they also use correlations based on similar plants. But instead of using the major equipment costs as the basis, they use major operating costs, raw materials, utilities, operating labor, and waste treatment. And now is when it all comes together. On the cash flow page, they combine the CapEx, the OpEx, and the revenue in an analysis to estimate the overall profitability of building the plant. Together, those 6 pages comprise the core of the model. The dashboard just makes it easier for us to interact with them. Let's look at a few of the pages more closely now. This is the process model page. And here's that process flow diagram. It would be a good idea for us to double check that this diagram is complete. Missing equipment is one of the biggest sources for error in this type of cost estimate. Next, let's skip to the equipment costs page. Here they estimate the cost for each piece of major equipment, and they do that by extrapolating from a known reference cost for a similar piece of equipment. The reference might come from a text, a database, or a vendor quote. Lower down, they also adjust the cost based on year using the CEPCI index, which is published regularly by Chemical Engineering Magazine. On the CapEx page, they use major equipment cost to estimate total capital cost. They use individual multiplying factors to estimate the various components. For example, they estimate that equipment installation will cost 39% of what the equipment itself costs to buy. Instrumentation will be 26%, and so on. This OpEx page is a lot like the CapEx page, but there's one item that we should touch on, and that's depreciation. Depreciation allows a company to write off the value of an asset over its useful lifespan. It can be a little confusing because it gets used in 2 different ways. On one hand, depreciation gets treated like an operating cost when you calculate all-in manufacturing costs. But on the other hand, it gets treated as a tax deduction when you're doing cash flow analysis. As we saw in Beth's presentation, they also integrated a tornado diagram with the model. Tornado diagrams highlight important input parameters and are a great way to visually represent a sensitivity analysis. The long green bar here indicates that single pass conversion is perhaps the most important technical parameter. Plastico will likely be focusing their R&D resources here. Monomer price is also high on the list, which indicates that it could be a risk, so we should probably do some research to see if we agree with their price projections. Alright, lastly, let's just take a look at this page labeled documentation, which probably would have been a good place to start under different circumstances. It's a good practice to document your models like this, to make them easier for others to understand, to help prevent them from being misused, and to serve as a refresher for yourself when you reference them in the future. They have things like the developer's contact information, a process description, and a list of important assumptions. They've also provided us with some information about their cost estimates, including expected accuracy, -30 to +40%, which is about what we'd expect for this level of cost estimate. Well, I think that's everything. We identified a couple areas to look into further, but it seems like Plastico has done their homework. You can download this video to use as a template from the Techonomics website. You'll also find other videos and resources there. See you next time.